So one example from starting from the previous lecture, like largest element of a vector. You know that the vectors, largest element of a vector. So suppose take a vector. So a function f takes an n-dimensional vector that is x1, x2, sorry, x3, so on till xn. These are the input. These x1, x2 up to xn are the elements of the vector. And if you take the element of the vector as input, what the function does, it gives you the maximum element of that. It gives you the maximum. Suppose, let us take an example, max of what it should be. Yeah, it should be 3 because it's a 3-dimensional vector, 3, 0, 1. And if you take the max, it's the max of each of the vector element. Similarly, max of say 2, 1, half. That. Max of 2, 1, 1 by 2. Huh? 3. But 3 is not in the element, right? I am only, this one is done. This one I am asking. Max of 2, 1, half. So you can see this is an element in R3. This is an element in R3 plane, like R3 space. Okay. Fine. So our aim is like that. Like if you have n elements, we want to take the max of that. Okay. Now my aim is this a convex function? Is this function convex? Is this function convex? You will see suddenly that this problem, which seems very abstract right now, will suddenly turn out to be a geometrically interesting problem. Okay. So this function, if you take the max, so max of x1 up to xn, is this a convex function? Any ideas? Is this a convex function? Okay, let me write with some masala in it. Okay, let me write in that way, where you see in books. Okay, like suddenly you see big notations in books. Right? Let me write in that way. So let me denote this vector x, which is x1, x2 up to xn. Okay. So f of capital like x vector is now the max. Okay, is now the max of E1 transpose x vector, E2 transpose x, so on, En transpose x vector. Do you think it's the same, one and the same? Okay, if you want to appreciate this, let us take the example of E1 transpose x vector. What is E1? E1 is nothing but 1, 0, 0, so on till n zeros. Okay. EI means all will be 0, all entries will be 0 except the ith position. So suppose this is 1, this is zeros. So this position is the ith position. All others will be 0. Is it okay? So therefore, now let us come. Now you know what is EI vector. Now let us come. What is E1 transpose X vector? E1 transpose means 1, 0 till 0. All elements 0. What is X vector? What is X vector? This is one row n columns. So if you want to multiply another vector, it should have n rows and maybe 1 up to you. Okay. So n rows, that x1, x2 up to xn. Yes. So can you tell what is the element here? X1. So isn't it this is nothing but x1? So you can see that when in books they write about this kind of things, they write in a very tedious way, but it's the same one and the same way. Okay. But why books write in that way? That's also matters. They don't want to increase the jargon. Why they want write in that way? If you see, these are all linear functions. Each of them is a linear function. Each of them is a linear function. Okay. So what you are taking is max of the linear functions. So each of them is a linear function, isn't it? X1, X2, X3, Xn. So these are linear functions. Fine. Now what you are taking lot of linear function and you are trying to understand what is the maximum of those linear functions. So maximum of linear function, is it a convex function? Yes. We saw in the previous slide. Max of two functions is always convex. Like you can see here, this function we took, this function we took, and we took the max that represents this guy here, which is this guy, and this is a convex function. This is convex. Because any two lines you take, 2 points you take, the black line is always above the pink. So therefore it is a convex function. You got the idea now. So the same thing I am doing it here. What I wrote is, now you are taking largest element of a vector. What I did is I wrote the elements of the vector as linear functions using E1 transpose X. So maximum, so this problem of largest element of a vector has been converted to, this got converted to this problem. That is, you are taking maximum of a set of linear functions. Okay, maximum of a set of linear functions. And you already know, if you're taking max of any function, it is always a convex function. Yes, so this also should be convex. Okay, let us see, because here you took non-linear. This guy was non-linear function, right? Non-linear function. But let us take linear. How linear function will look like? How linear function will look like? Straight lines. Linear function will look like straight lines, isn't it? Yes. So nothing, like we have to draw that straight. I don't know how this happens. Yeah. Let's forget. Okay, let's forget that slide. Come to this slide. So how this linear function will look like? Linear function will look like this. This is one function, isn't it? This is one function. How can we say L1? Maybe L1. This can be another function L2. It's a straight line, linear function. It can be another one, L3. It can be another one, L4, L5, L6. Yes. Now my question is it still convex? Let me remove some lines just to make you easier. Yes, so let's take these three. What's the max look like? Max of these three linear functions. We have to stitch it. Only though the max function you have to stitch. How you stitch? Yes, this guy is the max. This guy is not the max because it is below. This guy will be the max. Then this guy will be the max because this guy is above this and this. Okay. So this guy will be the max, right? Then which will be the max? These are below. So this won't be max. This line is above this and this. So this will be the max. Okay. Now this line is above this and this. So therefore this will be the max. Can you see? So this region, now can you say it is a convex? Yes. Because any 2 points you take, it is always inside that set. This is inside that set. So you can see that this is convex. Hope the geometrical idea is correct. Hope the geometrical idea is interesting to you. Okay, maybe I can show you one application to this, which came to me last night, just before this lecture actually. How we can go back? Maybe. hmm, I want to show where this case had arisen. Just an example, like, so that you can appreciate. What I take is there are a lot of one straight line, and I vary one parameter, and due to that, I see like a lot of straight lines which I want to show, and our job is to find common region, the common region regarding that. Yes. Yes, I wanted to show this to you. You can see this is a real life example where black line depends on the parameter k, and if you change this parameter k, like 14, 13, and all, the slope of the straight line changes. Like I am going from k to 15 to 20, so 15, 16, 17, 18, 19, 20. It went like this, so it is going like this, like maybe like this, yeah. 15 to 20, it goes like this. The slope varies. So therefore, you can see that it makes lot of intersections. Like as you increase 16, 17, 18, 19, 20. My aim was to find this common region. And how many vertices this common region has? Computationally, not eyeballing, computationally. If I give this set of, find me the area and the number of vertices. Okay. So this is where optimization comes into picture. And most importantly, you can see that this region is constructed by two functions. One is the maximum of these black lines. Can you see that the one half, this half, the below half is nothing but the max. It's nothing but the max of all the black straight lines. And this upper one is nothing but the minimum of all the cyan straight lines. So that both of these creates this region, common region. Okay. It's just a application, and you can feel that this region is a special region. Why it is a special region? This region is special because it's a convex region. Isn't it a convex set? Any 2 points you take in this set, it will always lie in the set, the linear combination. So it is a convex set. Okay. So maybe this example might arrive to you, okay, as a real life example. Maybe this example can be shown, and many sub questions on convex sets can be asked. Okay. So this is just one thing. Okay. So there are some more examples which we can cover, but I think like yeah, we can go. Okay. So you have function f of x, and what is our aim till now in this lecture, like so far in our course? What is our aim? If you have a function, what is our aim? Our aim is to optimize that function. Our aim is to optimize that function, and our aim is to find conditions under which that functions can be optimized. Yes. So therefore, suppose. So these are known as optimality conditions. These are known as optimality conditions for optimization. Okay. So you will see, given a data set to you, if you want to minimize the average of squares, then mean is the perfect candidate for that. Mean is the optimal solution for that problem. I will show you. So this is where some data science concept is flowing in. Then I will show you that for another problem, median optimal solution. Okay. So you see that how this suddenly median and mean are coming into the picture if you have a data set based on the techniques of this optimization. This is a small path you can see between data science and this small connection. Okay. So our job is to minimize one function, that is f of x. This is our aim throughout the course. Okay. So maybe I have turned to black. Minimum of fx. So we know x hat is an optimal solution. X hat is an optimal solution to this problem, to the problem minimum of fx. Okay, x hat is an optimal solution to the problem minimum of fx if what happens? You know that if it is a 1D function, what you do? If you want to find the optimal condition, set the derivative to 0. Set the derivative to 0. The local minimum will be those, or local maximum will be those points where derivative is 0 for 1D functions. Yes, those are the like known as the inflection points or extreme points. So this is for n dimensions, any dimension. If the story comes to any dimension, instead of a derivative, what you should use? Gradient, simple. So you have to check just gradient of f at x hat equal to 0. Okay, so x hat is an optimal solution to the problem min fx if the gradient of f at x hat is equal to 0. So this idea we will check. Why this works. First of all, why this works. Note that in the previous before the break we came to argue that suppose the function is not differentiable, then there was a definition to say whether a function is convex or not. So we told f is convex. F is a convex function if there exists a function g, okay, such that for all x you have f of y greater than equal to, yes, f of x plus dot product of g and y minus x for all values of y, for all y. Okay, this was the idea. Now I suggest, okay, can you put grad f. So grad f can be a candidate for this. Grad f can be a candidate for that g. Okay, so if you consider grad f value to be 0 now, what happens to this? Now you know grad f is 0, grad f at x is 0. So f of y is greater than equal to f of x. Now this guy, since grad f is 0, this guy will be 0 comma y minus x, which is 0. Okay, so what does it say? It says f of y is greater than equal to f of x hat, x hat for all value of y. What does it mean? So see, nothing I did. I used the definition and then I arrived at a condition f of y is greater than equal to f of x hat for all values of y. What does it say? F of x hat is the minimum. F of x hat is the minimum. So therefore, I am telling you how this condition is actually interpretable in different other conditions. Means the conditions are equivalent. Okay, the conditions are equivalent. Fine. Okay. So let us return now. Enough mathematical notations. Let us return to the data science question which I was telling you. Suppose you have different parameters a1 up to an, okay, and you have a data set x1 to xn. These are your set of points. N can be 10,000, n can be 50,000. 50,000 data set of points. Okay, suppose. Now my goal is find an x such that minimum of 1 by n summation of ai minus x squared is satisfied. Am I correct? Find an x such that minimum of 1 by n. So you can think of it as a sum of squares. Sorry, average of squares. Average of the sum of squares. Sum of squares, sigma ai minus x whole square. You are taking sum for all ai's. Okay, fine. And then you are taking the average of them. So this is going from 1 to n. Now what should be this candidate? Anyone? Ideas? What value of x will optimize this function? For what x? Any idea? Yes. See, the notation you will see will fuse you. Okay. But you have to remove that cloud and see what is the truth behind it. So if a function is, if a minimum of anything is asked, minimum of fx, see, I told you, minimum of fx is asked here. What you do? Gradient, you take gradient. You take gradient. So here we can take the derivative. You take the derivative and set to 0. Simple as it is. Can we take the derivative of this? Can you take the derivative? Idea. So idea is take derivative, take the derivative and set to 0. What you will get if you set to 0? Can you try? Can you try? So then, yeah, minus 2 by n summation of ai minus x, that equal to 0. So what will happen? Very near. Just you have to write it. Just you have to write it. You will see what x satisfy that. Something equal to 0. So you are bound to get x equal to something. Just take the derivative and set to 0. Derivative with respect to what? You should ask. Derivative with respect to x. Anyone? It should be done so far. Why is it taking? I want to know. This will give us a boost for a next example, next interesting example. So I want everyone to do this. Just you are one line away. You're just one line away. Anyone? What's the value? Yes or no? What? You need to find the value of x. Hmm? Yeah, we need to find the value of x. That's it. Yeah, maybe you can forget this data set. This data set not there. Only one value of x is needed. Don't. Yeah, simple enough. Mean of a. Done. What you do if you take the derivative and set? So what is fx here? Fx is, you are doing min of fx, right? So what is fx here? Fx is 1 by n summation I equal to 1 to n ai minus x whole square. So when you take the derivative and set to 0, what you get? Minus 2 over n summation ai minus x equal to 0. Isn't it? That should imply summation of ai minus nx equal to 0. Because you are summing x again and again n times. This guy is not 0, hence can be discarded. So my summation of ai minus nx equal to 0, that implies x equals to summation ai divided by n. That is nothing but mean of ai's. So if you take the mean of ai's, and put into this value, then it will minimize that function. So for a given data set, a1 up to an, if you want to take sum of the squares and take the average, you can take the mean of ai's, and that will give you the optimal solution. So can you see suddenly how mean came into picture? We were discussing about all differentiability, gradients, all those complicated things, Hessian, positive, semi-definite. But suddenly when you took a data set and you want to minimize, see, this function will definitely come in data science concepts, mainly in regression and all. When you want to reduce the error in regression, the actual data set and your regression line, if you want to reduce that error, You have to minimize that. Okay, when you can minimize, it tells you if you want to minimize this ai minus x whole square, okay, given a set of data points a1 to an, then the best candidate for you to minimize that loss is the mean of those data sets. Try to go home and see it again if it is mind boggling now. Okay. Okay. Fine. Let us go to the next question, which I have in my notes a lot of examples which I want you to read carefully. Then I have discussed about in my notes about ordinary least squares and lasso regression, where I have applied these concepts. I want, and the solution is there. I want you to go. I want you to go through and practice it. Don't just read it and keep it. Go, open the note, understand, and write yourself. Try to understand whether what you are understanding is actually happening or not. If you're not understanding, try to Google it. Try to Google it till the point you have understood it. Okay, so there are two more things, that is lasso regression, ordinary least squares, which I want, which is solved in my notes, which I want everyone to read it. The solution is also there. Okay. So I think Aman can share the notes today. Now itself we share in the groups or whatever. Fine. So just before that, let us come to one very nice problem. The nice problem I won't solve it throughout. I will solve in the midway and I will leave it. Okay, I will solve in the midway and I will leave it. Main reason being is I want to create that suspense so that you go and solve it. Okay. The idea is the answer to this will be median. The answer to this will be median. Okay, let us see. So what you did in this example, you took the summation of mean of the squares, a minus x whole square. Now, the similar question, very similar question, but you will be surprised to see this. Like, okay, sum of absolute values. Sum of absolute values. So take our aim is like given the values data sets a1 up to an, our job is to find the minimum. What x job is to find x such that minimum of 1 over n summation of mod ai minus x is achieved. Can you see now that here again we saw the modulus function? That means it will be non-differentiable. So suddenly the concepts of non-differentiability came into picture. So therefore it is important for us to know a differentiable function, how to optimize it. If there are non-differentiable function, how to optimize it. It is important. So now it is a non-differentiable function. So how we will go? It will help us. We learned it in this class, right? If it is non-differentiable, we cannot apply the known definitions already. So who helped us when it is non-differentiable? There were two most important guys. No, this is homework. It's homework for you. But this is just a fresh question. These are already solved. This is a fresh question. I want to know which two important guys helped you when the function is non-differentiable. Very, very loud. Yes, subgradient and yes, subgradient and subdifferential. That's it. Those two guys were the important guys which acted like differential even when your function was not differentiable. So therefore, these are subgradient and subdifferentials. So we will compute the subdifferentials and subgradient in this case because it is non-differentiable. How the mod function looks like. The mod function looks like this, a V shape. This is mod x. So here it is non-differentiable. Non-differentiable. So if it is mod ai minus x, if ai is positive, it should be like this. Ai. If it is negative, it should be like this. Okay. Miss Chakko, you are getting it. Okay. So how this should be achieved? Anyone? Hmm? Yeah. Observe that. Observe that I did one thing in the previous slide. We should motivate the idea in this problem. I took G to be zero. I took G to be zero here. I took G to be zero. I took G to be zero, and then the definition of optimality flows down. Okay, and G, what is G? G is itself a subgradient. Okay, so if zero is a subgradient, then it is an optimal condition. Okay, if zero is a subgradient, it is an optimal condition. This small observation brings us to a new definition, how we can use subdifferential to compute optimality condition. So this is the definition here. Like if you saw, if G was zero, then f of y greater than equal to f of x came, right? Again will come here. See, when we took G to be zero, then f of y greater than equal to f of x. This is nothing but saying that x hat is minimum. X hat is bringing the minimum of fx. When that happened when you took G to be zero. G to be zero. And what is G? G is itself a subgradient. So therefore, this motivates a definition which will be useful. Definition like, or a result you can say. Okay, or a result, like result. So you can say it like, for a non-differentiable function, I have defined a lot for differentiable function. This is one of the most important definition for non-differentiable functions. So for a non-differentiable function, for a non-differentiable function, say f, I think, yeah, f. I can write more generally. For a non-differentiable convex function. Fine. For a non-differentiable convex function, f of x. Okay. X hat is an optimal solution. X hat is an optimal solution to minimum of fx. To the problem minimum of fx. If this is the most important condition, if what will happen? If zero can be a subgradient, collection of subgradient is known as a subdifferential. So zero should be an element of a subdifferential. If zero belongs to the subdifferential, if zero belongs to the subdifferential of fx, subdifferential of fx can also be denoted as dou fx. So zero belongs to dou fx. One of the most important condition in optimization theory. Most important condition. So I suggest everyone to understand this part. Okay. So for a non-differentiable convex function f of x, x hat is an optimal solution to minimum of fx if zero is an element, zero is a subgradient, or zero should be an element of the collection of subgradient which is known as subdifferential. Okay. So subdifferential, I am denoting it by dou fx. Okay. Now this this definition you now know. My question to you is, can we apply this definition? Can we apply the above result find minimum of 1 over n summation mod of ai minus x. Got the point? Why we spilled the beans in this slide only? Because mod ai minus x is a non-differentiable function. It's a absolute value function which looks like a V shape. It looks like a V shape like this. So here it is non-differentiable. So if it is non-differentiable here and you want to find the optimum solution, can we apply this rule here? Can we apply the result here? Just think for, I will give you 1 minute. I'll give you 1 minute. Just think how it should work. Okay, just write like, just think 0, it needs to be an element of the subdifferential. Can you find the subdifferential of this function? That's it. Just okay. Let us be back. Let us be back. Okay, for a simple function mod z, for a simple function mod z, okay, this is mod z. Okay, let us compute the differential of mod z. Let us compute the differential of simple mod z. Okay, understood? Let us begin. See, we cannot take the derivative of mod z, but we can take the differential, subdifferential of mod z. That's the idea. If you are at, there will be 3 cases. Z less than 0. If z is less than 0, what is subdifferential? Subdifferential will be, just take the derivative as usual. For z less than 0, that means you are here. If you take a slope, what's the slope value? What's the slope value? Z less than 0, say that point. At that point, what's the slope? To check. To check. You understood the question, right? Z mod z. So z is less than 0. If z is less than 0, you have to take the slope. What's the slope? minus 1. How? Huh? Illa. Why? Why? What is the slope? You compute the angle with the x-axis. What is the angle here? Here it is 45, but you are measuring here. It is 135. Tan of 135, how much? Minus 1. So minus 1. So for z greater than 0, Mr. Chaco, z greater than 0, what should be the value? So you have taken a value here. What's the slope? Huh? Oh, now I know the secret. Okay. If z equal to 0, Mr. Chaco, z is equal to 0. If z is equal to 0, this is the interesting thing. Why it is non-differentiable? I told you. It is non-differentiable because at this point, you can have lot of different slopes. If the slope can be this, the slope can be this, slope can be this. Here, lot of things are possible. So, but the slope will be a number which will be between minus 1 and 1. It will be, because minus 1 is here, 1 is here, it will be somewhat in between minus 1 and 1. So it will be some w, some number we don't know. Okay, that's why it is non-differentiable. But that w we know it belongs to minus 1 and 1. So this is the subdifferential, how it is defined. You cannot write the derivative, but you can always write a subdifferential for a non-differentiable function. So this is the subdifferential. Okay. So this means that the derivative behaves differently depending on whether z is negative, z is positive, or z is 0. You getting the idea? Getting the idea? The derivative depends on the value of z, where it is. If z is less than 0, it is -1. Z is greater than 0, it is +1. Z is equal to 0, it is not defined. That means it can take any value between -1 and 1. Okay, this is how subdifferential is defined. Now let us come to our original problem. That is, we want to minimize this. If you want to minimize this, what's the definition? 0 should belong to the subdifferential of 1 over n summation mod I minus x. Isn't it? That's the necessary condition according to this definition result here. So 0 should belong to that differential. Now, can we find the differential? Can we find the differential? Any ideas? Can you tell me? Okay, let us compute the subdifferential of say ai minus x cap. What it should be? Ai minus x cap. Understand that this differential will be less than 0. Okay, when I want you to think in this perspective. Now you know the subdifferential of z. I want you to think subdifferential of this element here. Okay, so this depends. How you can think about it? That's my question. Hmm? Okay. So ai minus x cap is less than 0 when it contributes -1 to the derivative. When it contributes -1 to the derivative. Okay. Now it is greater than 0 if it contributes +1 to the derivative. Okay. I mean subdifferential. Okay. It can be equal to 0 when it contributes a value in between -1 and 1, which is similar to this case. Okay, fine. So I will tell you just the idea to you. After this, I won't solve. Okay, I will tell an idea to you. It will be at home task. The solution is given in my notes. I want you to understand this. I'm just telling you the logic. So there can be n elements. There can be n elements, right? ai to an, a1 to am. There can be n elements. Let m1 number of elements, m1 elements be such that ai minus x cap is greater than 0. Okay, that it is positive. Let m2 be some number of elements such that ai minus x cap is greater. M3 be some elements, number of elements such that ai minus x cap is equal to 0. Calculate these all elements. Okay, then what I suggest is you will come across the differential, that is the subdifferential. You need to sum these elements up. Okay, you need to count how many elements are giving you less than 0, how many elements are giving you greater than 0, and so on. You will come to know the final result will be the median of AIs. So if you take median of AIs, it is the best case, it is the x equal to median of AIs, which will optimize this. That is, if you put x to be median of AIs, it will minimize the sum of absolute values. So median of AIs, median of A1 up to AN, okay, minimizes the sum of absolute values of the data. I want you to work out from where I left. Okay, I want you to work out from where I left. I left here. I left from here. I want you guys to work it out. The solution is given. I gave you the idea. You calculate the number of elements. Okay, and convince yourself that median is the value which minimizes the sum of absolute values of a given data. if someone is giving you a data set and absolute values are being taken, and the person is asking you, can you minimize this sum? Okay, can you minimize this sum? Maybe that sum can be the money transaction. It can be the money transaction, isn't it? Like you can say the number of, like maybe you can give me an example, like maybe someone brought some shares in financial data analytics. I think you make a data set of this, like which user brought how many shares of which market, isn't it? You put it in a table, okay? And then my question is, if you take the sum of these absolute values of the shares, which is the money, which will always be positive, no need to worry about that thing, that absolute value. But my question will be, which can minimize the share, the sum of shares? Okay. So which value? Okay. So when you take the median of those data sets, it will be the guy which minimizes this, the sum of the shares. Okay. If you take the maximum to increase your, maximize your shares, you can take as minus of minimum of fx. I think you know this. Maximum of fx is nothing but minus of minimum of fx. Hope you got that idea. So if you do these kind of things, then yeah, it is applicable. So these are some methods where you can feel that somehow optimization and data science are quite interconnected. These are small glimpses. We saw how median comes into picture. We saw how mean comes to picture. It is solved in my what do you call notes. So there are 3 examples I left to you: lasso regression, least square, ordinary least square, and 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 this one, sum of absolute values. Okay, these 3 are solved in my notebook already. I want you to understand, read through and understand. Okay, fine, looks good. Okay. So yeah, I understand that it might be a bit clumsy, might be a bit difficult, but only by learning these concepts you can appreciate the bigger picture. Sorry, after one concept, we will go to Newton-Raphson method. That will be our first numerical optimization method. Okay. I will give you a problem in the class. That will be our last problem in the class today. And we want to solve it numerically. If you solve it, that will be a bridge to understanding gradient descent. That will be a first step to understand gradient descent, because gradient descent looks exactly like Newton-Raphson, but with a minor modification. Just doing Newton-Raphson, if you understand Newton-Raphson, you can understand all the methods. Okay, you can appreciate all the methods, because all the methods are just a tiny change in the Newton-Raphson, just a tiny change. We should not make this constant, we should make it adaptive. That will make you adaptive gradient descent method. Okay, no, we should not keep it fixed, we should vary it randomly, that parameter. Due to that, instead of gradient descent, you will name it as stochastic gradients. Okay, so don't worry that these will be very heavy concepts, these will be very hi-fi things. No, it will be just tiny change in some parameters, and we will be getting new methods. Okay, so yeah, that's our aim. But yeah, before that, like, let me explain you one more concept, one more visualization. I want your attention to be here. After that, we will move to Newton-Raphson. Here in this one, in this slide particularly, whatever I am going to talk to you might seem abstract, but here you will learn the power of gradient. Where I should go, see, gradient and all we are computing, but gradient is itself a vector. Gradient itself a vector, like it will give you a direction where to go. Okay, so gradient, I will show you that which way you should go to minimize your function. Can you give me an idea which way you should go to minimize your function? Which direction you should go? There should, see, I always tell you, I don't have that slide, but I will tell you as an example, maybe I have it. maybe remind me to show in the last part of the class, because this notebook is not yet saved. Okay, I will show you. Just remind me. There is a photo of myself where I'm climbing a mountain. Okay, and I'm at the top of the mountain, and my job is to go to the bottom of the mountain. Okay, and the photo is such a way that you will see a lot of direction you can go to. Okay, so which direction we should choose? That's the aim of gradient descent. I will show you that towards the end of the class. But yeah. We'll start with another concept that is which gives you a sense of gradient. This topic will give you a sense of gradient. This is after this topic we will learn Newton-Raphson and we'll stop. Okay, because I don't think we'll cover till anything more than that for this class. So this is something known as another important concept, that is tangent and normal cones. As usual, you have seen ice cream cones. Okay. How many of you are eating ice cream cones now? Till now? Still now, I am eating like ice cream cones. Ice cream cones. Adil also eating. Ice cream cones. Yeah. So how the ice cream cone looks like? You have something over here. Okay, that's like an ice cream cone. Yeah. So this is exactly the same concept. Tangent and normal cones. Okay. So we'll see why this is important. So now these are the concept where you have constraints. That means, yeah, you minimize this function, but you have to minimize within the boundary. You have to minimize within this rule. Okay. Like if you run a business in India, suppose you run a business in India, okay, then your like the sharing, like the selling of those products is limited within India. You cannot go outside India. But if you are an international market, you can go outside India. You can throughout the world, no constraint is there. So if you are a local businessman, your product is only within India. Okay, so the India is your boundary, India is your constraint. So that's what it is, constraint. Okay, fine. So some notation, this X, if you see, it is a space, it is referred to as a space where we want to carry out our optimization. Okay, where we want to optimize over. Okay, this is the space. This is the space X. Wherever you see this letter, it will mean that you want to optimize over that space. Okay, fine. What is tangent cone? What is a tangent cone? Tangent cone, I will write everything maybe in blue. Okay, tangent cone is the cone of direction. This is the cone of directions. Which is that we can move in, that we can move in. Okay. What is a normal cone? Normal cone I will denote in red. Normal cone, it is a set of vectors. So cone of directions mean also a set of vectors. Cone of direction also means a set of vectors. So normal cone is defined as set of vectors, okay, making greater than equal to 90 degrees, okay, with every vector in the tangent cone. Okay. Understanding, tangent cone is any vector space where we can move in, and normal cone are the set of vectors which are making greater than equal to 90 degree with the tangent cone vectors. Okay, got that idea? So normal will be perpendicular to the tangent. That's it. That's the basic idea. And we are in any dimension, so we are making this space, making this cone. Okay, cone can you have in 3D? Yes, cone you can have in 3D. Okay, cone can you have in 2D? No, you can just have a V-shaped thing. Okay? So this is referred to as a cone. If you want to visualize higher dimension, like 3-dimensional. Now let us draw some pictures. So tangent cone, if I want to denote tangent cone, I will denote it as a T on the space X where you want to optimize it. Okay. And at which point you want to have the tangent cone on that space, that is X, where X belongs to that space. Okay. Got the idea? I hope it is clear. You understood the notation. T is for tangent cone, where you want to have the tangent cone on the space X, that is X. And tangent cone at a point you need to have. You cannot have throughout. So that at a point X, that is a small point X. And that X, can it be anywhere? No. That's what I told you. It has to be in that boundary, local boundary, only within India. Okay. So X has a constraint. This is a constraint that it has to be only within X. This is a constraint. Okay. Got that idea, I hope. Now let us come to the tangent, normal cone, how it should look like. Normal cone is like this. It is N. Normal cone is denoted by N. Okay. Defined on this space X where you want to optimize point X. Obviously, X will be on that space. Okay. Got that idea. So far it is clear. Now let us visualize this. Let us visualize this with a figure. Okay. Very nice figure we will draw. Yeah. Maybe I'll draw it in black. Okay. Okay, so this is the space X. This is the space X. Suppose this is the space X. Okay. I want to find the normal and tangent cones, tangent and normal cones of this space X. I will take different points. So let us take this point. If this point is X, I want to find the tangent cones. What are the tangent cone? Tangent is this. This is the tangent, obviously. What is my viewpoint? Tangent cone is somewhere I can move in. Where I can move in? Any ideas? Where I can move in? I can move in only within X. I can move in only within the space X. Okay, so therefore, the points where I can move in, the vectors I can move in are these vectors. I cannot move in this way because it is not on that space X. Can you see why I cannot move this way or this way? I cannot move because it is not on the space X. So therefore, you cannot move in this direction. Okay. I hope you understood. So that collection of blue vectors you are seeing, that collection of blue vectors, if you want to assume this on the 3D space, can you visualize that it is like kind of making a subspace, like a half space in that region X? Okay. Hope you are getting it. Can you visualize this? Tangent cone is nothing but the set of all blue vectors. Tangent cone is the set of blue vectors you are seeing right now. Okay, so what is a normal cone to this? Can you see what is a normal cone? What should be the normal cone to this? Can anyone draw? So tangent cone, you learned that this is a total half space. The total half space. But then what should be the normal cone? Exactly. Can you say a bit more clear? And pointing where? But pointing to? Like how? Yes, yeah, exactly. 90 degree to that plane, 90 degree to that tangent. So it should be. Okay, so the blue vectors you are seeing, blue is tangent cone. Okay, and the red you are seeing is the normal cone. Okay, fine. Okay, let us take some other. Let us take some other points. What about this point here? What about this point here? How the tangent looks like? Yes. Mr. Fayez, I think, is excited about the tangent cone. Yeah, what should be the tangent cone? So at this point, you can see this is the tangent. Okay, at this point, you can see this is the tangent. So this is the space made by the vectors. This is the space made by, right? So this guy in blue you are seeing is the tangent cone. Okay, whatever you are seeing is the tangent cone. Now what should be the normal cone? Normal cone should be the collection of all the vectors which make greater than equal to 90 degree with the blue vectors. What can be? So don't suddenly think of the space of tangent cone. Draw one vector, draw several vectors, then you will know an idea how the tangent cone looks like. Let us take this vector. What should be the greater than 90 degree? Can it be this? Yes, it is greater than 90 degree. Can it be this? Yes, it is greater than 90 degree. So similarly, you can see that any vector you choose, okay, what vector will make 90 degree to this one? What angle can make 90 degree to this one? So all these vectors you are seeing are the normal cones. Okay, are the normal cones. Okay. So these are all visuals. These are all visuals. Let us come to optimization. Why we want this? Why we want this? So our job is to solve this optimization problem. Our job is to solve this optimization problem. Minimum of fx. Okay, minimum of fx such that x belongs to this space x, and this is the constraint. This is the constraint. Okay. So whenever we are discussing about these tangent normal cones, these are useful for constraint optimization problems, where you have a space on which you want to optimize over. Constraint optimization. So this is the constraint, minimize this. Okay. Now we know already that for x1, suppose x1 to be optimal, x1 belonging to this set x to be optimal, you need one thing, that is 0 should belong to the, for x1 to be optimal, 0 should belong to the subdifferential dou f at x. Okay. Now you will see how this guy getting transformed into non-differentiable cases. Okay. I told 0 should belong to the differential of f at x1. Okay. Okay, let us see. Okay, fine. So x1 is any point here. For that it is true. Now let us take x2. Suppose this point is x2. This point here is x2. Let us take optimality condition for x2. When x2 can be optimal? When x2 can be optimal. Location of x2. You know where how x1 can be optimal. That is fine. Now my question is how x2 can be optimal. What we should do? Any idea? Okay. So this is where this tangent cone and normal cone comes into picture. So to identify when x2 can be optimal. Okay. So you can see for x2 to be optimal, I actually need every other direction which I have written in my notes. I need every direction of allowable movement. For x2 to be optimal, I need every allowable movement. What does it mean to have every allowable movement? Can come, go, walk and come. Oh, yeah. Okay. Maybe this we will answer when you read all the previous part and come to class. Okay. So this is halted. This needs to be halted. No one is saying. I suggest everyone read it and come to the place where you can tell me what should I write when x2 can be optimal. Okay. Fine. So there we will see, but anyway. So this is halted. You should remind me next class. You should remind me next class. Okay, so everyone has calculator with them. Everyone. And you already took one semester with me. So everyone knows that it is mandatory in the class to have calculator. Now the calculator job begins. Okay. 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 So we have learned much of the right. We all the mathematical tools you need for optimization. Now we are ready to come to the methods. Okay. So this class will be like kept for the next class. Okay. After this, I will tell you what's the definition for this to do and what are projections. There is one more thing we did not cover, that is projections, which I will cover in the next class along with this. Okay, remind me. Remind. Okay. So let us come to Newton-Raphson. Newton-Raphson never leaves us. It helped us during root finding. Okay, how Newton-Raphson is so popular. Newton-Raphson helped us in root finding. Newton-Raphson helped us in fractals. Newton-Raphson helped us again in optimization. So Newton-Raphson method. Fine. So this is similar to root finding. This is very similar to root finding. Got the idea?